In this short video, I want to cover two things, as the title suggests. I'm going to talk about the significance of the numerical value of k, so this has to do with the size of k and what that means. And then I'm also going to talk about the position of the equilibrium. We can tell that, we can qualitatively talk about the position of the equilibrium based on the value of k. So we're gonna do that. Now, you hopefully recall how to write an equilibrium expression. And if you think about the equilibrium expression, remember k equals concentration products divided by concentration reactants. Then for a given reaction, large k means that the equilibrium, at equilibrium, there's a relatively large amount of product. Large k, product on top, that value must be large. It must be large in the concentrations, product of the concentration of the reactants at least. Conversely then, if you have a small value of Ka, what that means is that there has not been much product formation, so therefore a large amount of reactant relative to product. Okay, so again, already hopefully you can see from a qualitative point of view the value of K is going to tell us pretty well right away something about the concentrations of reactants and products at equilibrium. Alright, so let's look at this by way of an example. So here's the question. We have this reaction, nitrogen monoxide plus carbon monoxide yielding nitrogen and carbon dioxide, and we have this equilibrium value. So here's our K. K equals 2.2 times 10 to the 59. That's huge. That's a really big number. So considering the following concentrations at equilibrium, how can we arrive at such a large value of K? How does that value come about? Well, what I'm going to do is I'm going to give you about 20 seconds to write an equilibrium expression. So why don't you go ahead and write an equilibrium expression starting now. Alright, so hopefully in that 20 seconds you came up with a plausible equilibrium expression. It should look something like this. Equilibrium constant K equals concentration of nitrogen times the square of the concentration of carbon dioxide, products, divided by the square of nitrogen monoxide times the square of carbon monoxide, the reactants. Okay, so there's our typical equilibrium expression. Okay, with that equilibrium expression and our equilibrium concentrations, which again, part of the reason I highlighted this concentrations at equilibrium is because that's when you can substitute into this expression. With that, we can solve for K. We already know the value, but let's just solve for it. So 0.380 concentration of nitrogen times 0.760 squared concentration of carbon dioxide divided by 1 times 10 to the minus 15 squared times 1 times 10 to the minus 15 squared, the concentrations of the other two reactants. So when we solve that, we get 0.2194 divided by 1.0 times 10 to the minus 60. And solving for that, we get 2.2 times 10 to the positive 59. So we do get that huge value. So just showing you it can be looked at, it can be solved mathematically, and you get this really big value. And it should make sense because our concentrations of reactants is very small. Nitrogen monoxide, carbon dioxide, 10 to the minus 15 moles per liter. That's nothing. So really, very large K tells us the reaction favors products. And when it favors products, we say it lies to the left. Sorry, lies to the right. So the position of the equilibrium is to the right. Okay, so you should be able to start seeing, even just from the concentrations, where this equilibrium is going to lie. So, sort of summarized, if K is greater than 1, the formation of products is favored. Equilibrium lies to the right. Okay, higher concentration of products. If K is really large, like we just saw, the reaction is considered to be complete. All that remains in the reaction chamber is product. Now that's not entirely true. Again, that's sort of a generalization, but what it means is the concentration of products is extremely high, very, very much higher than the concentration of reactants. When K is approximately equal to 1, the concentration of products and reactants are approximately equal, and you can talk about the relative amounts of reactants and products being similar. Okay, so in the range 10, from 10 down to about 0.1 for the value of K. If K is less than 1, formation of products is not favored. Equilibrium lies to the right, or sorry, lies to the left, higher concentration of reactants. This is when K is less than 1. K much less than 1, no significant amount of product form. The reaction is considered not to have taken place. Again, generalization, you're always going to have a very small amount of product formed, but the concentration of reactants is so much higher, and that's when you get a very small value of K. Let's just look at one more example. So in this case, deconcentration of hydrogen bromide to hydrogen and bromine gases. So there's our reaction. And so two different scenarios. 700 K, that's Kelvin. The value of the equilibrium constant is 4.2 times 10 to the minus 9. So 4.2 times 10 to the minus 9. At 298 Kelvin, the concentration or equilibrium constant has a value of 8.3 times 10 to the negative 28th. So based upon these values of equilibrium constant, is the production of hydrogen gas more favorable at a higher or lower temperature? Essentially what that's asking is, which one of those values of K, given at a specific temperature, is going to yield a higher concentration of hydrogen? And so again, I'm not going to give you 20 seconds to write the equilibrium expression, but if you were to, in 20 seconds, hopefully you've come up with something like that. So now all we have to do is look at the two different values of K and look what they're related to. So at 700 K, at 700 Kelvin, our equilibrium constant equals 4.2 times 10 to the minus 9. And so that's, relatively speaking, compared to the other value of K, that's a large K. And so large K means, in terms of reactants and products, increased products. Okay, so if we look at the other value of K, so at 298 Kelvin, KQ is, I'm just going to write the exponent because the number doesn't really matter, 10 to the minus 28th. That's a very small K. And so when there's a small K, means decreased products and much more reactants. And so based on this, we can look at those two sort of scenarios and see that increased product formation, that's what the question's asking. Hydrogen gas is a product, there it is, hydrogen gas, and so this temperature with the corresponding equilibrium constant 4.2 times 10 to the minus 9 will favor increased concentration of hydrogen gas. Okay, so that's another way that you can kind of use that value of K to assess the system at equilibrium. And that concludes this video.